So, this is our third lecture on blast furnace material and enthalpy balance, and overall this is the 11th lecture of the course. So, this is the bottom segment of the furnace, and if you remember, so far I have developed the overall oxygen balance for an idealized blast furnace operation with our standard notation, which are all per mole basis these are all overall furnace parameter. Then we have the bottom segment oxygen balance, and that is equal to 1.26 is equal to NaC. The origin of the factor 1.3, as I have indicated to you, that we have beds of iron and beds of iron ore and beds of coke here, and the gas which is ascending through this, okay, and this is basically Fe. The solid material, the white one is our Wustite 947O, and the red one is the coke, and we have this equilibrium Fe 09.47O plus CO is equal to gas, and this is the solid, and that is equal to 0.947 Fe solid and CO2 gas. The temperature here is approximately 900 degrees centigrade, because that is the temperature at which our reduction reaction takes place, gas solid reduction reaction. So, which we have given an approximate value for the sake of convenience of calculation 1200 Kelvin. And as I have indicated with the blast furnace chemical and thermal reserve zone figures, how does the temperature of the gas and the solid varies, and we have shown that in this region the carbon monoxide, there can be assumed to be, I said that chemical equilibrium, actually there is a thermodynamic equilibrium, because we have temperature is constant. In that case, we have pressure remains constant here, as well as the chemical concentration remains constant, as we will see. So, all these three equilibrium essentially tells that there is solid liquid solid gas thermodynamic equilibrium in this Wustite reduction zone. And if you write down, assuming that the solids are in pure form, then the equilibrium constant for this comes out to be PCO2 pi PCO. And if you make an idealization that PCO2 plus PCO is equal to 1, total atmospheric pressure, there is nothing. In that case, what happened is we can calculate the delta G naught, this value, okay, and the value is, I think, 22,800 if I remember correctly, plus or minus 24.26 into T in absolute scale joules per mole of Fe. Okay, that is the value. So, substituting T is equal to 1200, we should be able to get the value of delta G naught, and this delta G naught is equal to RT ln K equilibrium. And if you substitute the value of delta T is equal to 1200, I think the delta G naught value will come out to be 1200 will come out to be something around 6600 approximately, okay, and then we can write down that K equilibrium is therefore is equal to 6612 or 6600 approximately divided by minus R into 1200. We can put the gas constant value, and this is exponential. That is what is the value. Okay. So, substitute the value of R. So, you can get the value of K equilibrium. So, you have the ratio of PCO2 and PCO known, similarly PCO2 summation of the two. So, you have two equations, two unknowns, and you can solve this to find out that the percentage of CO2, partial pressure of CO2 or percentage of CO2 will come out to be the ratio will come out to be, so this will give us the ratio is equal to 0.53 if we solve it, okay. And then we can PCO2 by PCO, okay, let us not worry about it, okay. I think so. What I have said that since gas constant is known, temperature I have substituted. On the basis of this discussion, I can therefore say that the K equilibrium is equal to whatever I have written here. So, K equilibrium is equal to delta G naught divided by minus RT, and since it is ln, so I would say it is exponential minus delta G naught by minus delta G naught by RT. So, you substitute R is equal to 8.31 and you get the value of K equilibrium. So, K equilibrium is known to you. So, therefore, PCO ratio is known to you, the summation of PCO2 and PCO is known to you, which is 1 atmosphere, an approximation. So, therefore, I would say that this will allow us to calculate the partial pressure of oxygen, and roughly again we are the values are a little bit different, but percentage CO2 will put out to be something like 30%. It is not actually 30%, the value will come out to be, PCO will come out to be 0.34 and PCO will come out to be, but for the sake of convenience we take it so that we do not, it is a classroom discussion. If you want to do take the more elaborate value, not 30%, but 34.6%, fair enough, that is the value is going to come, and if it is 34%, then this is going to be 66%, but again for the sake of approximation. So, if you have 30% CO and 70% CO and 30% CO2, so you can calculate on the basis of this, we will have an O by C ratio of the gas, which is the O by C ratio of the gas leaving the Wustite reduction zone is equal to 1.3. So, the value of 1.3 which I have indicated here comes from the consideration of thermal and chemical equilibrium of the oxidation reduction reaction that I have represented where, and I think I have erased that equation. So, that equation is Fe 0947O solid plus CO gas. So, we are talking of 0.947 Fe solid and CO2. So, that is we are talking about thermodynamic equilibrium of this particular chemical reaction which is taking place at this particular. So, it is here actually, that is the reaction. That is the reaction we are talking about. Okay. So, that explains now the value of 1.3. What is the origin of the value? So, therefore, I would say that the O by C gas, I make a representation, O by C gas Wustite reduction zone, this is a known parameter to me 1.3. And here as I have seen that we will put in 1.06 moles of Fe 0947O to get 1 mole of Fe. Okay. We are going to put in some moles of air blast, and then the coke rate is NaC, and that NaC is actually related to we can say NiC, and NiC as I have indicated is equal to your NaC plus whatever carbon which is dissolved in Fe itself. So, in the context of this equation, I have represented, I have said that look, if you plot oxygen O by Fe, oxygen per mole of Fe versus O by C ratio, a plot between this, because this left hand side essentially all terms are O by C, number of moles of oxygen in the blast per mole of Fe, number of moles of oxygen in the ore per mole of Fe. So, all these terms are and I have shown that y2 minus y1 is equal to NaC slope, and then this straight line, this I have already discussed. We have a straight line like this based on this equation, overall oxygen balance, where this term is 0, this point is 0 minus NOB and this I have already discussed, and this is, as I have indicated, is 1.5 for pure blast furnace operation, and this is the corresponding O by C gas. And this value, as we know that it has to come between 1 and 2. So, this is the overall oxygen balance line. Now, if we do the same thing for the bottom segment balance, then we would write down this equation, okay, represented it as 1.06 minus NOB, and again this side is O by C. So, this is also oxygen input, this is here it is O by C, that is what we are plotting. Okay. So, we get NaC, and then we have 1.3 minus 0. It is an oxygen balance equation. So, this is oxygen per moles of Fe, and if you multiply the O by C ratio with the active carbon rate, then this also becomes the active the oxygen, dimensionally they are consistent. The dimension of this and dimension of this and dimension of this all are identical. Okay. So, therefore, we can say that Y2 minus Y1 is equal to X2 minus X1, and which essentially tells us that this represents also a line, should be a line on the same figure, because we are plotting O by Fe and O by C, that is the plot that we have generated here. Okay. So, and since it is passing through 0 and NOB, and that the slope is same. So, the slope, as I have indicated, is the slope. So, if one of the point is identical and the slope is same, that means this essentially represents the same straight line, and hence we must say, we can say that there is a sacrosanct point 1.0, 1.3 and 1.06 through which, if this is 1, suppose, and then we can say that this is the point through which the second straight line must pass through. So, this point, which has a coordinate of, this coordinate is 1.3 O by C x and 1.06. That is the point we are talking about. This point, as far as this equation, these two equations are concerned, the plot indicates that this particular point is a characteristic point which will lie on the overall oxygen balance equation, or in other words, the overall oxygen balance equation and the bottom segment oxygen balance equation will collapse together into a single line, okay, having the same slope, and both the lines will pass through the point 1.3 and 1.06. That this parameter, this coordinate is derived on the basis of the Wustite reduction zone. This point is given a notation is equal to W. So, W point is a characteristic point of blast furnace iron making operation, particularly for those blast furnaces which exhibit a stable thermal and chemical reserve zone. We must understand that 1.3 and 1.06 is are values corresponding to some idealized blast furnace operation. As I have indicated, that this 1.06 could be 1.2 or 1.15 or 1.157, depending on whether there is metalloid reduction or not. Okay. So, the other oxygen input term will disturb this. So, for non-ideal operation, the point will not pass through 1.06, but you can find out what is that particular point. So, every blast furnace, as we will see, will have a characteristic line, and it will pass through a characteristic W point, which will have different coordinates for different blast furnaces. This 1.06 will depend on what are the kinds of ore material that we are charging into the furnace, what is the extent of metalloid reduction in the blast furnace, etc. Similarly, the 1.3, which is obtained on the basis of consideration of thermal equilibrium, this will depend on whether really it is 1200 Kelvin or not, or little bit less, what is the coke reactivity. Okay. All these kinds of parameters will tend to influence the value of 1.3. So, 1.3 and 1.06 are the idealized values, but it is possible to find out these two values given the characteristics of operation, given the iron ore, given the oxygen input, given the coke reactivity, given the Wustite reduction zone characteristic temperature. If you provide all these informations, then for your blast furnace, this particular coordinate 1.3, 1.06 can be assigned to their characteristic value, which may be a little bit different from the 1.3 and 1.06, which I have obtained on the basis of ideal blast furnace operation. So, now, we have three equations, and we have found out that there is overall oxygen balance equation is one, and the bottom segment oxygen balance equation is the other one, and we have three variables as I have indicated. So, we need, in the formalism, it is understood that if the blast rate is given to you, then by solving these two equations simultaneously, you should be able to find out that what is the coke rate and what is the top gas composition, because you have two equations and two unknowns. But if I can develop the third equation, in that case I can say that we have a fully predictive model, nothing needs to be given. We can, by solving the three equations, we should be able to calculate the NOB, the overall blast rate, the active coke rate, or the coke rate of the furnace, as well as the top gas composition. So, we will now turn our attention into the development of the third equation, and we will move on to the enthalpy balance equation. We must understand, if you consider that the furnace, if you consider an enthalpy balance over the entire length of the blast furnace, in that case what happens, at the outlet, we not only have an O by C gas, but we have a gas exit temperature also, okay? And that exit gas temperature is not known. On the other hand, at the if we compartmentalize the furnace into the two parts, we not only know the O by C gas composition here, but we also know that the gas is leaving this particular bottom segment at a temperature of 1200 degree centigrade. So, performing the overall enthalpy balance is problematic, because we introduce another unknown, which is function of the process and which is not known to us in the beginning, and that being the exit gas temperature, T exit gas. And what is this? We do not know. So, we introduce, in addition to these three unknowns, the fourth unknown. But we can see that the moment we restrict ourselves to the bottom segment output of the gaseous phase is essentially known to us, because O by C ratio is also known and the temperature is also known. So, therefore, the enthalpy balance that I am going to do is the bottom segment enthalpy balance. And it is again done in the steady state. There is absolutely no problem, as I have indicated earlier, that we do have a compartmental half section of the blast furnace or a part of the blast furnace, but that has no consideration, because we are taking into continuity of heat and mass, which is leaving one section and other entering the other section itself. So, long as that continuity is maintained, it is really does not matter whether we do an overall blast furnace enthalpy balance or a bottom segment balance, but that overall enthalpy balance I have been repeatedly telling we are not trying to do, because we will otherwise introduce one more uncertain variable. So, let us now concentrate on the development of the bottom segment enthalpy balance. This derivation is fairly long and it is complicated. So, without referring to my lecture note, let me make a honest attempt that if I can derive that equation or not. Now, derivation is tedious and derivation is long, not as simple as the oxygen balance equation, but it is important, because it will train you towards performing material and heat balance. So, this is the only elaborate exercise of heat balance that we are trying to do in this particular course, and I could have written the third equation in a straight away, okay, without going into the derivation, but that is not the objective, because in the disguise of the enthalpy bottom segment enthalpy balance, I will give you a comprehensive understanding of how to write enthalpy balance equation for a flow system. Before we do that, let us look at what is happening in the bottom segment. So, the bottom segment, I will now erase all these things and then try to tell you that what it is. So, this part is not there. Okay. So, let us start afresh. I have drawn the bottom segment of the furnace, and there is the exit gas. I know the parameter, that is the notation is Wustite reduction zone, and that is equal to 1.3. T gas, or the gas is leaving at 1200 Kelvin. We have iron bearing material, that is Fe 0947O, and that is entering at 1200, that is the temperature Kelvin. Similarly, we have carbon, it is an ideal operation. So, no gang material, carbon also, which is entering at 1200 Kelvin. This is the input. We have blast here. Let us say that the blast temperature, I keep it as a variable, as Tb is the blast temperature, which of course will be known to me. I can supply the blast at 800 degree, 900 degree, depending on the available resources as well as my understanding of blast furnace iron making, and it has NOB is the blast parameter, oxygen in the blast, but along with this we have NO NBN also. And in both these cases, to be consistent, O and N are the basis of my molar calculations, per mole calculations. We have 1 mole of Fe produced, which is in the liquid phase, and carbon, I have put a bar underneath carbon, which essentially means that the carbon is in the dissolved state, and this temperature I have taken it to be 1800 Kelvin. Typically, that means essentially 1523 or 1500 degrees centigrade, again for rounding off, these are elegant values, okay, because we will use thermodynamic data. Thermodynamic data are rarely available for 1211 degrees centigrade or 1324 degrees centigrade. They are mostly available either at 1350 or at 1400 or at 1450 degrees centigrade. So, that is why rounding off has given us this particular, it is an idealized representation. So, the liquid which is being produced here is at 1800 and which contains 4.3 wet percentage of carbon, which is dissolved in the liquid. So, let us see input. What are the inputs in the furnace and the temperature? So, iron ore, that is Fe 0947O, and the temperature is 1200, and all temperatures are in Kelvin. Carbon 1200, oxygen 1200, sorry, Tb plus temperature, nitrogen, that is Tb. So, this is carbon, this is Wustite or iron ore. Output and output temperature. Output we have hot metal iron, that is 1800. We have carbon which is dissolved, which is also in 1800. We have CO2 which is 1800, that is the top gas. So, these are the blast, ore and coke, and this is the top gas, and nitrogen, this is also CO2 and this is 1200, and nitrogen in the blast is also. So, this figure and the table that I have made are consistent. Okay. Output from the furnace, we know it is 1 mole, and that 1 mole is the 1800. Carbon dissolved, which is 4.3 percentage at 1800 presents, then carbon monoxide and carbon dioxide, which is there in the exit gas, and there I know that what is the exit gas O by C ratio, that is also known. Okay. So, this is top gas, and the nitrogen also we know. Now, so at steady state, input of heat is equal to output. That is our expression. Heat input to blast furnace is equal to heat output. So, we can say that we are charging 1.06 moles of FeO. So, I will say the first term will come out to be 1.06, standard enthalpy of Fe0947O. That corresponds to the iron ore that you have time to put in. What is the, so 1 mole of iron you have put in, okay, because it is a Wustite, so it is iron deficient, that is why we multiplied. So, this gives us 1 mole of iron. Then we have NiC, the number of moles of carbon per mole of iron, and this is the input which is coming in, and that is again H naught 1200, and because I have written it, so I will write it like carbon 1200. I will say, okay, next input is this is done, See, we will say, sorry, this is done, these are on output. So, this is done, this is done. Now, you have oxygen. So, NOB into H naught, then we say oxygen TB, that we have picked up the value of standard enthalpy of O2 and not O. So, therefore, I will put a value of half before NOB, because my oxygen is O. So, whatever is this we are considering, so that value has to be taken to be half of it, because this is O2 and this is O. So, similarly, I will have nitrogen, so half N, the blast parameter, which is the blast and nitrogen, and then again I will say oxygen H naught, nitrogen and Tb. So, these are the input of heat, okay? And now let us see what is the output of heat. So, most of the time, I mean in a live class, I mean I would make that lengthy derivation, and if I do a silly mistake of when I transpose or change signs, etc., the students would point out, but this being an online lecture, so and that I am doing it without any students. So, there is virtually no mechanism that if I do a mistake, it can get corrected on the board itself. So, I have to be really careful and move a little bit slowly. So, now let us see that what is the output. The output is 1 mole of Fe. So, we will say 1 mole of Fe, and that is H naught, and then we have Fe, which is liquid at 1800. Then we have carbon, which is dissolved in C by Fe, that is the amount of carbon per mole of iron, okay, that we have seen earlier. So, these are all terms are, and then we have enthalpy. So, this is carbon at 1800. The standard sign H naught is removed here, because carbon is not in pure state, it is in the dissolved state. So, the dissolution part is also taken into account. So, this is kilojoules, H will be given in terms of kilojoules per mole of carbon, and this moles of carbon will, so the term, every term is going to be kilojoules per mole of Fe, kilojoules per mole of Fe, all terms will have the same dimension. Second term is over. Then we have carbon monoxide, carbon dioxide and carbon nitro. Let us say that there is carbon monoxide 1200, and this is gas Wustite reduction zone. So, the number of moles of carbon monoxide, okay, which is going in the, and then we multiply it with H naught. So, this is N dot CO, I will write down gas Wustite, and this is H naught CO, the enthalpy of carbon monoxide at 1200 degree. And this enthalpy of 12, what does this indicate? this has 3 different components embodied, embodied into it. So, you take carbon at 1200 degree, oxygen at 1200 degree, then you combine together. So, the standard enthalpy of carbon plus the standard enthalpy of oxygen, and then the heat of formation, those are the 3 terms that are embedded. And now, whether you start it from 500 degree, go to 1200, from you have say you have to select from which temperature you do, because we know that these parameters are not going to be related on what you call the path which is taken. So, whether for example, if you look at iron, whether the heat content you will be applying at 1200 degree or 1800 degree, that has nothing to do. How we approach the final state, once the initial state is there, final state is there, whether you are travelling this way in order to calculate the heat content, or whether you are calculating this way to calculate the heat content, it has nothing to do, because thermodynamic properties, as we know, are not a function of the path, it is a function of the state, and so on and so forth. But it is important for us to note that this term will contain 3 different parameters, as I have, or 3 different enthalpy terms, as we will split this later on. And then we have a similar term Ng, Wustite reduction zone, and then we have CO2, okay, and then we have H naught CO2 1200, because that is the temperature at which the gas is living. So, I want to calculate that, and then on top of that we have nitrogen, and that nitrogen is going out half NOB, sorry, NBN, and H naught, then it is not going out at TB, it is nitrogen, and it is going out at a temperature of 1200 Kelvin. That is what it is. So, we have the 5 different terms, one heat content term, the another enthalpy term, third term, fourth term, 5 terms. So, I see that. So, if you make in any heat balance problem, if you just make a table input and output, and then you establish the equation, you will never do a mistake, you will never omit a term. So, I see 4 terms should be there on the left hand side, which is the input, under input heat content, and 4 terms should be there on the right hand side of the term. Now, we will make certain simplifications here. This table is now has served its purpose, so I can erase this. We know that this term NiC, for example, is going to be equal to NaC plus C by FAM. That is one simplification that we are going to do. We have the second simplification, that the moles of nitrogen and moles of oxygen, they are related. Okay? So, I would say that in this case, the simplification that could be allowed is NBO by NON. So, that is going to be equal to 0.21 by 0.79, or I can say that NON, the number of moles in the blast, NOB, this is. So, NO, N and B in the blast is equal to 0.79 by 0.21 into oxygen in the blast. That is possible. So, that we can have homogeneous terms, all terms will be in terms of oxygen. There are several stages of simplification. Okay. Also, we know that NgCO2, this I have already given to you, that NgCO, for example, I can, Wustite reduction zone need not be written, it is, I can say that this is equal to NaC into mole fraction X CO. So, mole fraction of CO in the gas Wustite reduction zone. And then we can say that NgCO2, Ng the Wustite reduction zone CO2 is equal to NaC into x mole fraction x CO2 gas Wustite reduction zone. But in the first lecture itself, I have shown you that the mole fraction of, for example, x CO2 in the gas mixture, in the carbonaceous portion of the top gas, could be written in terms of O by C in the top gas minus 1, and x CO can be written in terms of 2 minus O by C the gas. If you sum them up, then x CO, mole fraction of CO plus mole fraction of CO2, if you add them up, this O by C will cancel, 2 minus 1. So, that has become equal to 1. So, this is consistent relationship, and that I have derived already in the case of this. Okay. So, therefore, if we substitute this, then we can say that this is going to be equal to NaC into XCO, which is equal to 2 minus O by C gas Wustite reduction zone. And similarly, I can say NaC, which is equal to O by C gas Wustite reduction zone minus 1. So, therefore, the third simplification that I am going to put is in terms of this parameter and in terms of this parameter, which I have represented as NaC into, this is carbon monoxide. So, this is 2 minus O by C gas Wustite reduction zone and bracket closed. And this term is going to be NaC multiplied by O by C, this is carbon dioxide. So, this is equal to O by C gas Wustite reduction zone minus 1. That is the simplification. So, simplification 1, simplification 2, simplification 3, this is the first stage of simplification. We are trying to arrive at a very elegant form of the equation, and that is why we are doing all these things. Now, if you look at this, so therefore, I can say that there is going to be one, therefore, now if you look at this equation expression, okay, there are following this simplification, I want to do one more simplification, and that is what I am trying to see, and that simplification is going to be exclusively with respect to the blast term. In the blast, as you can see here, that we have NOB and NNB terms. So, I can make all these terms in terms of NOB. So, with respect to the NOB terms, there is going to be one NOB term here, one NOB term here, and there is going to be one NOB term here. If you look at this expression, okay, for example, that nitrogen term is there at 1200 degree, and the same term nitrogen is there at TB temperature. Okay. So, this is the same term, because from this term I can manipulate half NNB term can be taken out, and then I can represent this term if you transpose it, H naught N2 TB minus H naught N2 1200. But I cannot cast the oxygen term in that particular form, okay, because there is no counterpart of the oxygen term. So, I am going to add one term, oxygen term, and subtract another oxygen term, so that I can have. So, in this equation, now what I am going to do, I am trying to get, for example, here one term I am going to add and one term I am going to subtract. The same term I am going to subtract. So, there is no problem in the overall oxygen balance equation, I am trying to put it in a elegant fashion, and that addition term, because this is the same term I am going to add. So, I am going to add half NOB H naught O2 instead of 1200, and then I am going to add this half NOB H O2 1200. So, there is no consequence of this addition and subtraction term. Now, you can see that I can transpose this term here. So, I will get HO2 minus TB, HO2 comma TB minus HO2 1200. Similarly, if I transpose this term to the left hand side, I will get something multiplied by H naught n to T b minus H naught n to 1200, and I will be left with one additional term, which is going to be this additional term I have generated. So, therefore, let us now transpose these terms, okay, and let us see what happens. So, let us take this term now to the left hand side and manipulate with this particular term. So, what we are going to get? Then we are going to get something like half NOB is common, okay, and then we have H naught oxygen Tb minus H naught oxygen 1200. That is what we have gotten. Then we take this term on the left hand side and manipulate with this term, and then we get here plus half N O. So, this is going to be N, and then this is going to be blast, and this is going to be HO2 sorry H naught nitrogen Tb minus H naught nitrogen 1200. That is the results of, and this term is on the left hand side, and I can use that simplification to here, substitute it, and then I can say that look, this term is going to be actually, so let me not NOB, and then I can say that look, because this term is NOB is equal to what? We have NNB, sorry, this is NNB, nitrogen blast, and this NNB is equal to 0.79 by 0.21, okay, into NOB. That is what it is equal to. So, I can now write this term in a compact way, like I will take the NOB term common, okay, and then I will have one bracket is here H naught O2 Tb comma Tb minus H naught O2 1200 bracket close, and then I am going to have, there is a half term is also there. So, I can put the half inside, okay, I will not take the half common, and then we have so NOB is taken common. So, this is half, and then I have here also half into 0.79 by 0.21 into H naught O2, and then I have N2 Tb minus H naught N2 1200, and the bracket closed. So, that is what this turns out to be. So, NOB is taken out common. So, you have the factor of half here associated with the enthalpy terms, that is what it is. Then in addition to half, you have 0.79 by 0.21, that is also associated with this, and this term essentially now you can see this is called the enthalpy of the blast term. Whatever is within the bracket, okay, apart from this whatever is written here, and this term is nothing but the enthalpy of the blast. Enthalpy of the blast, this term is positive provided Tb is greater than 1200. On the other hand, if Tb is equal to 1200, then this enthalpy Eb term is going to be 0. On the other hand, if Tb is less than 1200, it is obvious that the Eb term is going to be negative. What does that indicate? That indicates that if you inject the blast at 1200 degree centigrade, that each of the component in the blast goes out whatever oxygen was there, that oxygen is going out to 1200. So, the blast has neither contributed to any heat, nor it has absorbed any heat, and because its temperature is 1200 degree centigrade. On the other hand, if you consider that the blast temperature is more than 1200, then the NOB EB term is going to be a positive term, and that means the blast has contributed supplied heat to the blast furnace itself. So, through the blast heat can be supplied to the furnace, or the blast itself can absorb heat. There will be demand, thermal demand, that yes, you have supplied the blast at 1000 degree centigrade, and look, the blast is to be heated at up to 1200. So, I have to now, this demand has to be fulfilled. Thermal demand of the blast is that you have supplied it at 1000 degree, and then you want it out at 1200. So, therefore, it is to be heated up. So, you have to supply heat to the blast, or there is a demand of heat by the blast, so that the blast can be discharged at 1200 degree centigrade. So, we will for the time being consider that the value of the blast is either 0 or it is a positive quantity. That means, the blast supplies heat. The blast does not require to be heated, but in turn, because it has an excess temperature of more than 1200 degree or at least 1200 degree. So, the overall contribution of the term EB, enthalpy of the blast, into NB, NOB, is taken to be a net positive term in the system. Therefore, I can now say that, look, I have transposed this. So, I will not write the equation since I have shown it here. So, let us erase this particular term here. Okay. Everything I am erasing, I am retaining this. This term is also, and then this term, the simplification of the blast term is here, EB into NOB. All the 4 terms, and this, as I said, these I have transported already to the left hand side, and so I am left with this additional term. So, if you remember, one term I have added, one term I have subtracted. The added term is taken to the other side. Okay. So, therefore, this term I have added on the left hand side itself. And then, if I can write down now, so I can write down like NaC into the carbon monoxide term. So, we have 2 minus O by C, gas Wustite reduction zone. So, it is the same thing I am writing here, okay, bracket close, and that is equal to the number of moles of carbon monoxide and H naught into CO 1200, and then this is plus NaC is equal to O by C, gas Wustite reduction zone, minus 1 into H naught CO2 1200. We will make another simplification here. So, all the simplifications we are going to now. So, it is NaC plus C by Fe m, that is how NiC has been substituted, and this is H naught 1200, or first I will write carbon and then 1200. Now, the time has come. There are 3 compounds here. As you can see, Wustite is one compound, carbon monoxide is one compound, and that the temperature, gas temperature is known, or the constituents temperature is known. Since the heat of formation data is available to us, time has come now to split this enthalpy into 3 different components, split this enthalpy of the compound in 3 different components, and this into 3 different components. Okay. But before that, we will also like to see that this input output, I will say that we will like to recast this equation in the demand and supply form also. and that will be explained in the next class when I continue from this particular point itself.